Okay, let's get into this. Welcome to the deep dive.
Glad to be here.
So today we're looking at something, well, pretty surprising based on the material you shared. We're digging into how complex math, specifically calculus, pops up somewhere really every day.
Yeah, extracting juice from fruit. Seems simple, but the math behind it gets interesting.
Exactly. The sources focus on things like pineapple and mango and how differentiation and integration apply.
Right. Tools you usually think of for, I don't know, physics problems or engineering.
For sure. So our mission today, using this source material, is really to unpack how these calculus concepts help figure out the rate juice is extracted, how fast it's actually coming out.
And that's a key point, isn't it? Why do you need to know the rate? If you're designing, say, a fruit press or just trying to get the most juice efficiently.
Like for a mango or something.
Exactly.
Yeah.
Understanding how quickly that juice is flowing at any specific moment, well, that helps you optimize everything.
Okay, so how does the math actually do that? The sources point to differentiation, right?
Right. Differentiation is all about rates of change, instantaneous rates. So think about squeezing that pineapple.
Hmm.
As you apply more pressure, more juice comes out over time. You can measure the total volume collected.
Okay, that makes sense. Total juice versus pressure or time.
Yeah. But differentiation lets you take that relationship, total juice versus pressure maybe, and calculate the exact rate the juice is flowing out at any specific pressure level.
So not just the average speed, but like the speed right now. Milliliters per second at this exact moment.
Precisely. You model the total volume, then differentiate that model. Find the derivative, mathematically speaking,
Yeah.
and that derivative function gives you the instantaneous rate. It pins down how fast things are changing at one specific point in the process.
Wow, okay. That's actually pretty cool. Using calculus to figure out the best way to squeeze a mango based on flow speed.
It moves it from just, squeezing harder to understanding the dynamics.
The sources also mention integration, though. How does that fit in? It's kind of the opposite of differentiation, isn't it?
It is, yeah. It's the inverse. So if differentiation gives you the rate, how fast it's flowing now,
Integration lets you work backward.
sort of. If you know the rate function, maybe how the flow rate changes over 5 minutes, integration lets you calculate the total amount of juice you've collected during that time.
Ah, okay. So rate gives you the speed, integration gives you the total volume accumulated over time.
Exactly. They're two sides of the same coin, really. Both give you a piece of the puzzle for understanding the whole extraction process mathematically. Differentiation for the right now, integration for the how much overall.
It really does show how this stuff, calculus, shows up in places you just wouldn't expect.
Definitely.
So to kind of recap from the sources we looked at, calculus, especially differentiation, gives us a tool to precisely calculate the rate of juice extraction from fruits like pineapple and mango.
And integration helps figure out the total yield over time. It connects this, well, fairly advanced math to a very practical, almost basic agricultural process.
It's not just theoretical curves on a graph. It's about optimizing something tangible, something real world.
Mm-hmm. That's a surprising link.
Okay, so here's something to chew on maybe. If calculus, differentiation for rates, integration for totals, is useful for something like getting juice out of fruit,
Mm,
where else?
right.
Where else might these powerful math principles be working away silently under the hood in everyday things all around us that we just don't even think about?
Makes you wonder, doesn't it?
Definitely something to think about.